Well, good afternoon, everyone. Hope everybody's enjoying themselves at Oracle Code today. So for the next 45 minutes, we're going to spend some time talking about some improvements we've made in G1. And when I'm in your shoes and I'd go to conferences and I would sit in the audience, I always kind of walked into sessions saying to myself, I hope there's one thing I can learn here that I can take away and I find useful. So my goal today is that you find at least one thing in what we're going to talk about that you found useful. The standard Oracle disclaimer here, which basically says, don't believe a word I say. So once we leave this room, just forget everything that we talked about. So what to expect here, we're going to take a look at the G1 GC features and improvements that we've made in JDK 10, at least what I think are the most important ones, or the ones that I think that you'd have the most interest in. And we'll also take a look at what I think you could expect in terms of improvement in performance. Performance being throughput, latency, and footprint. We'll probably also have some time to take a look at a subset of what I would consider some of my more favorite things that I'd like to see us do with G1 that are coming beyond JDK 10. A little bit about myself. I'm Charlie Hunt. I actually live local here. I live up in Libertyville. Over the last 10 years or so, I've been leading a variety of different Java SE and JVM projects at Oracle. I've largely been in the performance area. I've been doing performance work since probably the mid-90s. I've held a lot of different roles as a performance engineer or performance architect, both at Oracle and previously at Sun. Also spent a little bit of time at Salesforce.com as their performance engineering architect. A few years ago, myself and a fellow by the name of Binu John wrote a book called Java Performance. Some really good information in there about how to go about tuning a JVM. You could take a lot of the information in there and apply that to G1 as far as the approach and methodology goes. The second book that I co-authored with a couple of other folks who worked on G1, myself included, is largely centered around G1. So the Java Performance Companion, if you're in this area of working with G1 and you have some needs to tune it, it's an excellent resource. It's largely dedicated to G1. So here's our agenda. So we'll talk about two of the major improvements in JDK 10 related to G1. The first one being full GC is now multi-threaded. And the second one is called faster card scanning. And I'll get into, and I'll do a little bit of explaining what that means. And then we'll get into this future list, and then we'll do a little summary at the end. So some background here on this full GC for G1. So in JDK 9, we made G1 the default collector. Full GC and G1 is single-threaded in JDK 9. And previously, of course. And if you got to this state in your application where it was going to have to do a full GC, it was single-threaded. So you had this sort of undesirable experience of having a long GC pause. And this was a relatively long pause compared to what you would see with parallel GC, also known as a throughput collector. The implementation of the full GC in JDK 9 for G1 was largely based on serial GC, which is a GC that's been around since we started Java, and it was single-threaded. So it used a lot of the pieces from serial GC. So that's kind of the background on it. This feature was called JEP 307, Parallel Full GC for G1. So you might be asking yourself, what's a JEP? JEP stands for a Java Enhancement Proposal. Anybody can write a Java enhancement proposal. Any one of you can write one. So if you have an idea of how we could improve Java or the JVM, you can write one of these and you could just submit it for consideration. So that's essentially what a JEP is. It's a way of saying, hey, I want to propose this new capability or a change, usually larger than something like a small enhancement to a Java class or something of that nature. But it's a way that you can propose a feature enhancement. So JEP 307, the 307 was the number that was assigned to this feature capability. The key improvements, of course, being a multi-threaded mark compact GC for G1, for doing a full GC. So it's the same idea as far as what parallel GC does when it does a full GC. So this sounds a little bit confusing when you talk about a parallel full GC for G1. Sometimes that gets confused with what's called parallel GC, which is known as the throughput collector. So that's why I wanted to throw this up here, is to try not to enter that confusion into parallel GC versus the multi-threaded G1 full GC. So multi-threaded being the notion of parallel. Okay, so from an implementation side, it really wasn't as easy as taking serial GC or its single-threaded implementation, adding threads to it, and then guarding around the states with some locks, or its shared state with locks, or some compare and swap sort of concurrency idioms. It's not quite that simple. And it's not as simple as dropping in parallel GC's implementation of multi-threaded GC. G1 and parallel GC have vastly different frameworks. You probably have worked with applications at your company where you have two different frameworks, but yet you have some functionality you'd like to share between the two, but you can't because they're two just totally different frameworks underneath of it. That's in essence what the scenario is between G1 and parallel GC. So some of those differences arise from the design or the architecture of G1 versus parallel GC. In G1, you take this Java heap and you're dividing it up into a large number of equal-sized regions, where with parallel GC, and you're taking a young generation and an old generation. In G1, you take a set of these regions and they become a virtual notion of a young generation heap or an old generation heap. So there's some vast differences in their implementation. Some of the other things that are a little bit more of a challenge is it's a little more difficult to compact the area of memory where your Java objects are when you have a large number of regions versus you have a generation space that you'd have in parallel GC. G1 also has to deal with, which is kind of an artifact or a side effect of having these regions and the way that the Java heap is split up. You have this notion of a remembered set, and we'll talk a little bit more about what a remembered set is and what its role is. But you have to update these, so there's more work to do because you have a larger number of these regions to deal with as opposed to dealing with an old generation space or a young generation space. And then there's also this notion of having to update a lot of things because you're moving objects. Parallel GC has to also do this sort of thing. So as you're moving stuff around in that Java heap, you have to update references when they're pointing to other things that are getting moved. One of the limitations which we'll talk about is work stealing. So work stealing is this notion of you've got multiple threads here that can do work, and you have to figure out some way to divide up this work where maybe you've given something to one thread and it goes off and it's executing, and there's another thread that's doing some work and it's got a lot more work to do. So one thread completes and it's waiting for the other one to finish. So work stealing is this idea of saying, hey, if you've got some work over here for me that I can do because I'm not doing anything, give me some of that and I'll continue to work on that. That's essentially what work stealing is. GC, we didn't implement work stealing just yet. So, and we're going to address that a little bit later. So that's one of the things that you're going to see a little bit later here is we did address that, or it will be addressed in a future release. Okay, so here's kind of a complicated chart here, and I'll kind of walk you through this. So this is kind of showing what the relative performance difference is here between parallel GC and G1's full GC. Over here, if I can get this thing to show up. Is my pointer not working? Let me walk over here. So over here on the far right, I guess I can't quite see that. A little faint. Okay, there it's showing up. Over here is there's three different apps here that we're looking at, or three different types of a configuration of tests. This top one is a test where it's doing, in essence, the test is implementing or enforcing a certain number of system.gc, so it's invoking a full GC. And it has a relatively small live set, a fairly small Java heap, so it's on the rather small side. There's another one here that's called Big RAM Tester. It's a least recently used type of cache stress test. It's got a lot of references. It has a rather large live set in it. 90% is pretty large. A 10 gig Java heap. So this is a pretty good stress. And there's another one called Tree Fragger, which is a fragmentation-inducing type of benchmark. So it's inducing fragmentation in the Java heap. And this was something that was developed by the folks at Red Hat. The amount of live data that's in the Java heap is in this sort of what I would consider a medium size. And it was run with a 20 gig Java heap. So if we look over here at the chart then, G1 is this darker blue, parallel GC is this lighter blue. The way to look at this scale is this is normalized to G1's performance. So anything that's higher here is going to be something that's performing a little bit, it's actually taking a little bit longer. So in this case where it's invoking system.gcs, it's actually, parallel GC is actually taking a little bit longer to do this than what it is for G1. Similar over here with the big RAM tester. When we get over to the fragmentation, the tree fragger, we can see in this particular case, G1's actually a little bit slower than parallel GC. And this kind of goes to that classic notion of, with a given implementation of some kind of functionality, you can think of different algorithms that, depending on what you're doing as far as what it's asked to do for work, where it might execute a little bit faster, one versus the other. You know, I could write an application where serial GC could probably execute it faster than any of the other collectors, but it'd be very specialized towards serial GC. That's kind of what you see over here. Here happens to be an application where parallel GC actually runs this faster than G1. Likewise over here, these happen to be a couple of applications that run faster with G1 versus parallel GC. So it's going to vary depending on the application. In terms of command line tuning, what you need for command line and any tuning info, this multi-threaded full GC is on all the time. You can't turn it off. There's no command line option that says, here's how you turn it on or turn it off. It's just on all the time. Nothing for you to do, nothing you have to turn on. Your knob that you can control here is the number of parallel GC threads. So parallel GC threads is the number of worker threads that work both in the case of a full GC, but also in the case of other types of GC events, whether it's a minor collection, a young GC, or on any other type of G1 pause, whether it's an initial mark, etc. For logging, a good place to start is to start with this, the first one here with the xlog GC with the star. This is similar to what you would have been familiar with print GC details. Thank you. Get a little better pointer here. If you want more detailed on these full GC phases, you could add this, what's over here on the far right-hand side. It's not necessary unless you kind of want to get into the gory details, or if you're a guy like me where you kind of want to understand what's this thing really doing, how does this work. This will give you that sort of detail. For fine-tuning G1, this is applicable not only for full GC, but also other places of G1. A rather long sort of command line option. You can take the output from this. If you're stuck with understanding what it means, you could then turn around and ask one of the experts at Hotspot GCUs at OpenJDK. And even if you're stuck, you can go there. More than likely, somebody will probably chime in and say, hey, can you collect this information using this set of command line options? Depending on the description that you come with, they might have a little bit shorter command line options there for you. In terms of limitations or potential consequences, As I mentioned, there's no work stealing, so the time to complete could be a little bit different depending on how the work is distributed to those worker threads that are doing the full GC. And that's going to be largely dependent on what those object graphs look like. So we addressed this in JDK 11. This was one of the first things that we wanted to work on. And I'm going to talk about that a little bit later. You have potentially a higher usage, Java heap usage after the full GC versus that single-threaded implementation. And on average, it could be as much as a half of a region waste per GC worker thread. Now, that might sound like a lot at first, but consider in G1, you'll have over 2,000 regions versus that number of parallel GC threads. Think about something like a 16-core hyper-threaded CPU. Think of that as a system. You got 32 hardware threads there to deal with. Even in that case, you've got 32 GC worker threads versus 2,000 regions. Is that something really to be worried about? That's not a lot of space that you'll be talking about in terms of waste. So an obvious thing here is the smaller number of GC threads, the less this waste would be. So if you only had one of these, it's in essence, you got the equivalent of what you'd have with the single-threaded full GC. So what we did in JDK 11 was we introduced this notion of a dynamic sizing of GC worker threads, which turns out saves us Java heap space because we don't have this wasted space, because it'll dynamically tune itself to figure out what is the most appropriate or an appropriate number of GC threads to be running. And it also saves on native space. So a couple of reminders here. Yes, this multi-threaded full GC is in JDK 10. This dynamic sizing of these worker threads is something you'll see in the next release. And as I mentioned, we'll talk more about that a little bit later. So this gets us to the faster card scanning. So what's a card? Well, let me see if I can explain this for you. So this is going to get into a little bit of some technical detail. So what I've got here is these big blue squares. These represent what is a G1 region in memory. These little gray spots in here, these little rectangles, these are representing an object that's been allocated in one of these G1 regions. And these arrows are something that says, here is an object that's making a reference to an object in another G1 region. So here we've got several of these guys. So these arrows are something that's representing an object that's referring to another object in another region. Okay, so when G1 does a garbage collection, it'll evacuate live objects in one of these regions to an available region over here. So think of this as an available region. It's going to evacuate this object to here. So it's moving this object here. Notice that there's a reference here that's going to need some updating. So there's something that needs to track this mechanism or that these references exist. That's in essence what's called a remembered set. So in G1, you'll often hear this term or terminology called remembered sets. This is one of the key pieces with G1 as you start talking about tuning it and whatnot, is remembered set. So this remembered set is this thing that keeps track of the inter-regional references. So as this object is getting moved, there's an update that needs to go on in this remembered set. So the thing that keeps track of this is a thing called a card. So a card is, in essence, a little subdivision of memory that identifies that these sorts of references will cross into another region. There's a similar sort of thing that exists with the other collectors. So it's a notion of identifying when there's references between other objects and they cross outside of an area. Is in essence what a card's purpose is. So when you're going through a GC pause, one of these things that you're doing is you're scanning these cards. So the faster you can do this, the shorter your pause time becomes. So that's what this feature is all about. So as I was just saying, GC needs to find these references in these cards and these remembered sets on these moved objects very quickly. So the way that we did this is we took a look at the code that does this, and we saw that it was rather generic. And we replaced this with rather specialized code and highly optimized. And in essence, we removed a lot of the branch conditions in it. One of the things that you will run into as you work with processor people that make processors like Intel, is this notion of branch prediction or branch misprediction. So the more branch conditions that you have in a program, the more opportunity there is for mispredictions. So if you're able to eliminate some of those conditions, your code begins to execute faster. So that's, in essence, the principle that we applied here. So on this graph, the way to look at this graph is, this is a graph that's, in essence, a little more complicated than what I'm going to describe here. Think of this as a plot of GC pause times. So when I overlay the before and after, this is kind of hard to see, but you can see a little bit of a difference in the shade of green here, where this was after we made these changes of the implementation of the card scanning. So you can see there's a rather substantial difference in the pause times. So what you can expect to see here is you should expect to see faster or shorter card scanning times in JDK 10. In other words, expect to see shorter pauses, or you're going to see less frequent pauses. You're going to see one of those two or possibly both. Okay, in terms of command line tuning, there's really nothing here to do. You get it for free. There's no command line option. There's not any tuning that you need to do to realize this. For logging suggestions, it's pretty much the same as what we saw before. Limitations or potential consequences, I'd be surprised if you're going to see anything here. You should just have a positive experience with this. But if you do see some issues here, do let us know. So reminders here, both G1, multi-threaded full GC and faster card scanning is in JDK 10. Let us know if you've seen any issues. Here we'll get into the future list. This is some of my favorite things, a couple of things we'll look at here of things that I'd like to see us do and things that we've worked on that you should see in the next release. So one of them is dynamic GC worker thread sizing. So this is the thing that helps us with the work stealing also. So manually setting the right number of GC worker threads it's a hard task, and it's a time-consuming task. There's a lot of stuff to consider. How many hardware threads do I have? What's the underlying hardware? How many other apps are running on this system? What's the application? How many threads can it have busy at a given time? Does the application go through different phases where it might need additional threads to deal with GC? It's hard. And we only have a small set of knobs that you can set, but we got multiple ones. So they could be setting parallel GC threads, the concurrent threads, parallel reference processing. Those things are all set statically, and that number of threads are going to sit around for the life of that app. The benefit of getting this right is you save resources, you have faster startup, you potentially realize some pause time improvements. The solution to this is G1 collects all sorts of information already. How about letting G1 figure this out for us and let it dynamically change this as the application goes through different phases? You might expect that as an application initializes, it probably is allocating a lot of objects and could probably use a lot of GC threads at initialization time. As it transitions and gets into a steady state, it may not need as many GC threads again. It may be able to do just fine and maybe even better without having as many. So G1 tracks all of this different information ranging from the actual bytes that have been copied into GC, how many references have been processed, how many reference objects are processed, how many cards were scanned. There's all sorts of stuff. So these two charts, we'll start with the left one over here. So what we see here is this lighter blue is before we made this change to do dynamic sizing of the number of GC threads. This is this lighter one. So this is the before and after. This is pause time. This is a logarithmic scale here. So this is pause time. This is overtime. And you can see this here as we're starting and initializing, our pause times are a little bit higher. And then we start to flatten out here. But notice that our pause times are consistently lower here. Over here on the right is the number of threads that we're using at each GC. So early here in time, we're using a large number, and here's where we're setting it statically, and they're sitting around for the life of the app. That's what's happening today. Here, what we're doing is we're letting G1 figure out what is the optimal number of threads to be running. And we can see this drops very, very quickly. All right, so how does this help? Well, it's an enhancement to G1's full GC. It addresses this no work stealing limitation. It improves the JVM and the app's initialization time. And it typically reduces the JVM footprint because you don't have as many of these GC threads sitting around that are in essence, they're not helping you. They're reducing memory footprint. There's some additional information here if you want to take a look at this. This is all documented in JEP 308 under this G1 ergonomics, and this is the, in our bug tracking system, this is the actual bug number that you see associated with it. So this should be in JDK 11. It's actually been implemented already. So if you haven't access to an early access build out there, you can try this out today. The one thing I tell you is keep in mind that disclaimer where I said at the beginning, don't believe a word I say. So this gets us to the next one. This one I'm pretty excited about too. So there's a thing called the remembered set. So we talked about this role of what this remembered set plays in G1. The problem with this is remembered sets can occupy a lot of memory. One of these remembered sets abstractions exists for every region that's in G1. So you could have 2,000 or more of these. And in some cases, we've seen this take as much as 20% of the total heap. In other words, of the memory that's allocated for the Java heap and for the JVM, as much as 20% of that going towards this mechanism of the remembered sets to track these inter-regional references. That's a rather alarming number. And you find that the old regions use the most remembered set memory. That kind of makes sense because those are the objects that sit around the longest. And the longer something sits around, you would expect other things to reference it. So that makes sense. So that's the problem. A couple of the key observations here are, I just mentioned that it maintains these for all of the regions, but they're not required. We don't have to have them for all of the regions. We really only need them for the regions that we're collecting. The regions that we're collecting are also known as a collection set. So this is a G1 terminology. So if you see this terminology and something you're reading about G1 and it says the collection set, that's the set of collections that are, or the set of regions that are being collected on the current GC. Sometimes you'll see it called a C set. So that's really the only place that we need these remembered sets. The other thing that we can do is, if we're maintaining these remembered sets all the time, we have to go through this notion of once we've collected a region and we've updated the remembered set, there's probably some obsolete entries in there that are no longer needed. And we have to do some cleanup work there. Okay, is there some way that we can avoid doing that? Well, the solution was, or the solution is, let's only keep these required remembered sets around when we need them, and let's just dynamically build that when we need it. And because we only need it for that set of collections that we're, or the set of regions that we're collecting. And that's much smaller. So in other words, we don't have these 2,000 regions that we're ever going to collect on a single GC. We got a much, much smaller number of those that we're going to collect on a GC. So why don't we just construct it for that set of regions? The other advantage here is it also helps minimize some memory fragmentation. So this is memory that's being allocated natively for the remembered sets. So what we can do here is we can construct these remembered sets concurrently between G1's remark and its cleanup phases. And then instead of this, this live map calculation that we were doing, we also don't need to do this updating and maintaining of these obsolete entries. Because once we're done with this, we can throw it away. Because we're just going to rebuild this remembered set each time that we do a GC. So there's none of this obsolete entries that we need to do. So the potential consequences of this approach are, it's going to lengthen the time between G1's remarked cleanup phase, and it could be up to 30% longer on a marking cycle. But G1 has a dynamic notion of identifying when it should start a marking cycle. So IHOP here stands for initiating occupancy percent. So it dynamically figures out when it should start a marking cycle. G1 can automatically figure that out even though it may take 30% longer. So it can just start the concurrent cycle a little bit earlier. So you might see a little bit higher CPU utilization during those times when it's doing this concurrent cycle. So that's one of the trade-offs that you'll see. What I would say is probably well worth the benefits because you're saving potentially a lot of memory. So this bounds, it gives you an upper bound on the amount of memory that you're going to use because that number of regions that you need the remembered sets for is much, much smaller. A nice side effect of this is it also improves throughput and lowers pauses because there's less work to do during the pauses. So on this big RAM tester that was on one of these earlier charts, the memory usage here was about 10% of the maximum heap size. After this feature was implemented, it dropped to about 7.5%. So it was a nice substantial change. There's an industry standard benchmark that I run very often, and then I have some things that I use to inject some additional behavior to it that I beat up on a lot of GCs with. And when I ran that on this feature, on this change, its throughput improved by almost 10%. This workload also has a notion of application response time in it. It's actually a geometric mean of a couple of different app level response times ranging anywhere from, if I remember right, something like 10 milliseconds to 200 milliseconds. It had a 10% improvement in its latency. That I was really impressed with. I thought those were pretty impressive numbers. So here we had a feature that we were able to reduce memory footprint, we were able to increase throughput and reduce latency. That's very, very unusual to realize a benefit in all three of those areas. That usually requires a lot of work. So I was really, really pleased with what I saw with this. Some additional information on this is you can find this in this bug number here. Again, this should be in JDK 11. Again, remember that disclaimer that I mentioned at the beginning. Don't believe a word I say. To summarize this, JDK 10 has this multi-threaded full GC. You're going to be able to realize faster, shorter pause times from the faster card scanning. A couple of the new additional enhancements coming in G1, this dynamic GC worker thread sizing, the rebuilding of memory remembered sets, and you're going to be able to realize that lower memory footprint, the higher throughput, and lower latency. A call to action here for you. Go check out JDK 10. Just released today, as you've heard. We'd love to hear your feedback. If you liked what you saw with what I talked about with JDK 11, there's some early access builds out there. I'll leave this slide up here when we finish, or I'll go back to this slide. I just have one more after this one. And these slides are also going to be available online from what I hear. So you'll also be able to get a set of these. So one of the things you can do with JDK 11, for instance, is you could do some early qualification on those features if you got an environment where you can do some testing. It's kind of a nice way that you can do some early qualification, so when it comes out as a release, you know you can hit the floor running and you can do that upgrade right away. If you're looking for something that has lower latency, a project that we started, actually this has been under work for several years now, that we just recently open sourced, is called ZGC. ZGC is a low latency GC that's targeted. I rarely see something over 5 to 10 millisecond pause times with it. For anything larger than that, I have to write something very specific and really beat on a given area of pauses within the JVM to get something outside of 5 to 10 milliseconds. From a stability standpoint, I'm really pleased with what I'm seeing with this thing stability-wise. So if you have an opportunity to kind of want to take a look at that, if you're looking for something in that lower latency area, go check that out. A couple of people I wanted to acknowledge that were really helpful in getting this slide deck together. A couple of the G1 engineers, Thomas Schatzel and Stefan Johansson, and really everybody from the Hotspot GC engineering team for their efforts in improving Hotspot, and also the OpenJDK community. We get a lot of contributions from people, whether it's their experience as far as what they're seeing with an app, questions that they ask, tuning questions, code contributions, etc. So a huge thanks to those folks. So I'll leave this back up. We've got about 5 minutes here if some people have some questions. Yeah. So we're talking about the number of, what's the ideal number of GC threads? Is that what we were talking about? Okay, so the question is around, is there a number of ideal parallel GC threads to use? That's going to vary some based on the underlying hardware and also on the application. And what I mean by that is, I'll start with the latter part of that. As you saw in that chart, when an app's going through initialization, you see an awful lot of objects being allocated, and the system is very busy going through that initialization phase. You expect that it's going to be able to want to utilize a lot of GC threads because it's allocating very, very quickly. It's doing a lot of work. And then as it transitions into that steady state, where it may not be using a lot of that CPU, I think most apps, when they're running in production in a steady state, might be using 25 to 30% of the CPU. Maybe a number of around 25% of the total number of hardware threads might be a more optimal number of parallel GC threads at that point. But as it transitions into a stage, like it goes into like a busy hour or a busy period, you might want to see that number increase. So it's that's kind of how it varies there. Where the underlying hardware comes in is you can have systems that have a different number of underlying hardware threads. You also have different CPU architectures where that may also influence the number of threads that you want to have. For instance, on Spark systems, they have a much larger number of hardware threads than, say, an Intel or an AMD system. So if you have a very, very large number of hardware threads, when the JVM starts and you've got a large number of parallel GC threads, it influences the time it takes for the JVM to start because it's having to start all of these GC worker threads also. So there's there's a couple of moving pieces in there to figure out what that ideal number is. Yes, it can. And different CPU vendors, as I was saying, for instance, you take Intel, typically you have 2 hardware threads per core. That's a hyper-threaded core. There are systems that Spark makes that can have as many as 16 hardware threads in a core. So it can vary a lot. Where in the Intel case, maybe as you're going through initialization, you might want the same number of hardware threads as the number of GC worker threads. In the case of that Spark system, because of the difference in the chip architecture, you're not going to want 16 hardware or parallel GC threads for each one of those hardware threads, because not every one of those hardware threads are going to be executing at the same time. It may only be 50% of that. So that's a rather hard question to answer, but those are the 2 variables, the 2 largest variables in it is the application behavior and the underlying hardware. Other questions? Yeah. So the question is, how many GC threads are started by default? Oh, I used to know this number off the top of my head. If I remember right, it's in the area of, it's a formula along the lines of 5/8 the number of underlying hardware threads, if I remember right. It's in that area. I didn't hear all of that. It's not a fixed number for every system, the same for every underlying piece of hardware. It will look at the underlying hardware to see how many hardware threads there are, and then it'll apply this formula. It isn't exactly 5/8 the number, if I remember right. But the formula is very close to that. Typical region size, it can be anywhere from 1 megabyte to 32 megabytes. 32 megabytes being the maximum region size. So when G1 starts, it'll look at the Java heap size that you have specified, and it'll say, okay, ideally I'd like 2,000 regions. Okay, so if I have a 2 gig Java heap, okay, that's going to be a 1 megabyte region. When I get to a rather large Java heap, on the order of 100 gigabytes, it's going to use a 32 megabyte region, and you might have more than 2,000. Yeah, it'll always target around it'll target 2,000 depending on the Java heap size, and then it'll use in multiples of powers of 2, 1, 2, 4, 8, 16, 32. But 32 is the largest size. Yeah, so what it'll do is it'll take multiple regions. So the term that G1 gives for that. So the question is, if you have an object that's larger than a region size, what does G1 do? So G1 will treat that region as something called a humongous object. So this is a terminology that you'll see in the tuning information about G1 that you'll run across, is they'll talk about humongous objects. So a humongous object is an object that's larger than, or it's an object that spans more than one region. So it'll take multiple regions, put those together to hold that humongous object. Yes? I don't know if I could put an actual number on, percentage-wise, or what the actual the delta would be between, say, JDK 9 and JDK 10. Some of the areas where I know there would be rather drastic improvements are, there's a certain set of family of applications that will allocate one really large array, or they've got a really large hash map. Those are things that are rather hard for a GC to go through and mark, because they can be very, very deep and very lengthy to go through and mark. we've done a lot of work to improve how we go about marking that or stealing to be able to mark that in a shorter time. That's one of the big improvement areas. Okay, I think that's it. Thanks everybody for coming.